Hello to all of you. As I completed yesterday, I will make a video on plate girder. This is numerical video of plate girder. So let's the problem to explain. Design the welded plate girder from effective span of 30 meter and carrying a UDL of 30 kN per meter over all the span and concentrated load also of 150 kN is acting at 10 meter from the both ends. It is fully restrained at both ends throughout the span. So we have to understand at first how loads are acting. This is the effective span of 30 meter. Then it will, and the UDL will be at only 30 meter. This is extra for both hands, and it is 30 kilonewton per meter, and also two concentrated load at 10 meter from both ends. This is 10 meter, this is 10 meter distance from both ends of both concentrated load, and this load is of 150 kilonewton. You can see in the question 150 kilonewton. This is a diagram of this, and now we will calculate step by step to design this plate girder. So step first was assume self-weight of girder. So we will write here calculation of factored load. Calculation of factored load. As know, W equals to W1 plus W2. What is W1 and W2? Here I will explain you. Then the W1 is factored load. This is 30 UDL. Should we have to factored by multiply by 1.5, and it will be 45 kilonewton per meter. And what is W2? In the previous design step I have told you W2 is WL by 200, but that is not WL by 200. This is W by 200. You have to cut L from there. Sorry for this mistake. You have to factor also, so I am multiplying by 1.5, and W will be 30 is usual UDL and acting on 30 meter span of, you can see, plus 2 concentrated load of 150 also divided by 200. So it will be 9 kilonewton per meter by calculation. So we can find out W, which is factored UDL. Factored UDL. This is calculation of factored UDL, and the W will 45 plus 9, which is 54 kilonewton per meter. And we will also find in first step factored point loads, or we can say factored concentrated load. Then the first load and second load will be similar. This is 150 to be factored multiplied by 1.5, which will 225 kilonewton, or similar. So it will also 225 kilonewton. Now we have to calculate step second, calculation of shear force and bending moment. So calculation of shear force and bending moment. Shear force, as we know, here is UDL and point load both. So for point load, for UDL, this will 54 into 30, which is the span, effective span divided by 2, plus the concentrated load is 225, and by the calculation it will 1035 kilonewton. And the bending moment, it will also 54 into WL square divided by 8, 54 into 30 square divided by 8, plus 225 into acting at 10 meter from both ends. So bending moment will be 8325 kilonewton into meter by the calculation. This is shear force, this is bending moment. Now we will find out step third, which was calculation of size of web plate. Calculation of size of web plate. So I want to tell you what is the size of web plate. That's d into tw. D into d or tw. If you will use into here, that means it will area of web plate. So d optimum depth d equals to bending moment m into k divided by fy, as also have discussed in the design step of plate girder in the previous video. So you can there you can see there, assume k equals to 120. This is the value of k have to assumed by the IS 800 2007. It also be in the middle of 80 to 120. You can choose any one value. As I chose 120, but you can choose instead of this anything. And the m is, I have find out 8325. So I will write here 8325 into k is 120, which is depth factor, and fy we know 250 to the power 1 divided by 3. So it will, and we also multiply by 10 to the power 6 to this, because this is in kilonewton into meter and have to change into newton meter. So this will give answer 1586.87 mm. And so we can take nearest value, take d equals to 1600 instead of 1586. This is a design. You can choose the desired value. As we know, k equals to d upon tw. By this, tw will be d upon k by the replacement of these two. And we know d equals to 1600, which is g, and k be assumed 120. So we will get 13.33 mm from here. We will also check this value from clause, the value of tw from clause 8.4.2.1. This is 8 from the page number 959. Then we will get from there tw equals to 12 mm, which is nearest value of this. There is no problem to take 12 mm of tw. Hence provided wave plate will be d into tw. That means so 1600 mm into 12 mm. Now we will all calculate the step number 4. Calculate size of flange plate. Which is VF into TF. This is the area of flange plate. So that means we can also understand we have to find out VF and TF. What is VF and TF? At first we will calculate area of flange by this formula. This formula is m into gamma m naught divided by Fy into D. So we will put all the values 8325 into 10 to the power 6 into 1.1, which is value of gamma m naught. Fy, this is 250 and this is 1600 evaluated in the previous step. And AF will be now 22893.75 mm square. As also we know AF equals to VF into TF. So we can get BF equals to AF upon TF. AF upon TF from here. So it will VF equals to if we will put the value of AF, which is 22893.75 upon TF, we can assume this as a first equation and consider the flange is plastic. There was a three conditions in the design steps I have already told in previous video, which was condition for plastic, compact and semi-compact. Then we will consider here, consider the flange is plastic. This is not requirement to check. This is condition to find out the value of VF. Flange is plastic. Then we know that B upon TF, which I have already discussed in previous video. What is V? V, that's BF divided by 2 into TF, should be less than or equal 8.4 epsilon. Then BF upon 2 TF, after replacing 2 here, it will 16.8 epsilon. From equation first, we will put the value of VF, this value, to here. Then what it will, 22893.75 divided by TF, and 1 TF is also here, so it will square of this, and 16.8 epsilon replaced from to this, it will 22893.75 divided by 16.8 epsilon TF square. Epsilon is 1, so you can write by this 22893.75 divided by 16.8. Then TF square will be, by the calculation, 1362.72, and TF will be, by the square root, 36.92 mm. We can take the nearest value, 40 mm. Should be less than or equal. So BF equals to AF upon TF, as we know, and the value of AF is 22893.75 divided by 40. So VF will be 572.34, or maybe take 580 mm, the nearest value. VF also have to checked by 0.3 into D, 0.3 into D equals to 1600, and it will 480 mm. So I have already told you in the previous video, we will take the value of VF, which will maximum, and you can see here that the 580 is maximum value, so it will be used for everywhere VF. You cannot use this value, and hence provide flange, hence provided flange plate will be VF into TF, that means 580 mm into 40 mm. And now we will check about step 5th. Check for minimum web thickness. Check for minimum web thickness. Then here is a step A, serviceability check. Serviceability check. We know D upon TW or DD upon TW should be less than or equal to 200 epsilon. We can find out the value of D, which is 1600, and this is 12 TW. Should be less than or equal to 100, which is also having this. Okay, satisfied by the serviceability check. Then the step B of fifth, check for compression flange buckling. Check for compression flange buckling. Then we also know D upon TW should be less than or equal 345 epsilon square. We can check this by this value will not change, so it is also satisfied. Okay, satisfied for the compression flange buckling check. Okay, now we will move to next step number 6, check for moment capacity. Check for moment capacity. Then we have to assume first, assumed wave is thin. I have discussed already in the previous video what is thin and thick. About to find out ZP. 2AF D minus TF divided by 2, where is AF equals to 2BF into TF D minus TF divided by 2. What is D? D equals to small d plus 2 into cover, visible both side of small d. So we will calculate ZV equals to 2 into BF, which is 580. 2 into BF. 2 into BF, 580 into TF. TF is 40 into capital D minus TF. Capital D minus TF. D equal to small d plus 2 into cover. Small d is 1600 plus 2 into cover, assumed 40. We can assume less than or equal 40 and maybe more than 40, and minus TF divided by 2. TF is also 40 divided by 2. Then the value of ZP will be 38.08 into 10 to the power 6 mm cube. Then MD have to check with maximum bending moment, and our maximum bending moment was 8325, and we have to find out MD. What is the MD? MD is beta B ZP Fy upon gamma m naught. We have to put the value, and beta V is 1, ZP have find out 38.08 into 10 to the power 6, and Fy is 250 divided by gamma m naught 1.1, should be greater than from 8325 or equal maybe. Then by the calculation it will 8654 point something. Then this was in Newton mm and I have changed in kilonewton meter, so we can see this is satisfied. Okay, then this step is passed, and the next step number 7, as we have discussed, this is needed or not. So I wanted to just tell you what was step number 7. Step number 7 was check for lateral torsional buckling, which is not required for here, so we will not check this. Check for lateral torsional buckling. Check for lateral torsional buckling. This is not needed. I will move to step number 8. And what is step number 8? Step number 8 is check for shear capacity. Check for shear capacity. And we know shear capacity VD should be less than from V. Sorry, greater than from B. So we will find out VD at first, and capital V is known. Then VD equals to AV into FY upon root 3 gamma m naught. Then VD have to find out what is AB. AB equals to D into TW. This is not AV, this is AW, area of web plate. D into TW into Fy upon root 3 gamma m naught. VD equals to 1600 into 12 into 250 by putting all the values root 3 1.1. Then we will find out VD equals to 2519.3 kilonewton, and which should be greater than from V, and V was 10352515.3. You can check which is maximum and what was condition to be maximum. And where I got this, I wanted to tell you, this was in step number 2, 1035, which was CS4. And we will move for last step number 9. Check for web bearing. Check for web bearing. We know that Fw equals to V1 plus N2 Fy Tw gamma Mw. So we know here is also point loads or moving load. Both are not, but point load is here. So we have already discussed B1 will be 0 and N2 will be 2 N2 instead of N2. And what is N2? N2 is 2.5 TF. That's will 5 TF. Then we will find out Fw, which should not be less than from V. Fw is V1 0 plus N2, that means 5 into TF 40, and Fy is 250 and Tw is 12 divided by gamma Mw 1.1, which is 5454.54, and we will also divide it by 1000 to this to make in kilonewton, so it will 54.45. So we will check for this condition should not be less than or equal from V. In the design step I have already told, but V is 1035, so here 545.45 is less than or equal V. That can say V is greater. This design is failed in web bearing. Now we have to provide the stiffeners in this, so we have to provide and bearing, or maybe say load bearing stiffener, which I will tell you next video. So thank you.